Hello everyone, this is lecture 8 of PTRE 475575. Well, completions and advanced stimulation techniques. I'm recording from my office today because, like I said in the announcement, I had to attend an industry lunch. So I had to miss our lecture, so I'm recording now to make it up. And we lost last Thursday also because of the I was in Houston for HFTC. So we are about more or less the point where we are wrapping up module 1. And I did post the homework, which I put it due on Monday night. Now, Monday is a holiday, it's President's Day. Let's see where we stand. I expect to go over the homework next week. Next lecture on Thursday. I will go over it quickly. If there is still trouble, and there is a lot of students complaining about that, I'm okay moving it like to Wednesday night maybe. But as of now, let's keep it this way. Sadly, we don't have an audience now because I'm recording privately, but I'm not. It's not the normal lecture time, like live lecture. Otherwise, I would have asked if you guys have seen the homework and where you guys are standing, more or less, and I will actually help a little bit. But next lecture, I will probably go over it very quickly and see where we stand. But as of now, it's gonna be due on the 16th, Monday, 11:59 p.m. at night. So last time we discussed about we finished seeing the polygons, then we started looking at the near wellbore stresses. We went a little bit deeper on that. That was from 2 lectures ago. Then we talked about how do the fractures open, and we said that it's very important. It's the most important concept of this class, how fractures open. We said that a fracture is like a page. It has long dimension, height, and then width. The most important aspect, geometric aspect of a hydraulic fracture is the width. It opens always by doing work against the least in situ stress at that particular location. And that was Hubbard and Willys' paper from 1957, who revolutionized a revolutionary paper that came up with this concept. Before that, people were arguing. Some people were saying all fractures are horizontal. Some people were saying all fractures are vertical. Hubbard said they can be either horizontal or vertical. It depends on the stresses. And they will always open against the least compressive local stress from the point of initiation. We did talk about that and drew some sketches on the class. Then we said that when you have the wellbore, you create force perturbations in the stresses in the near wellbore region. So when you go to drill and then you fracture, you may encounter a stress that is different than what you anticipated. So you went to drill and the region was stressed with as VSH max SH min. But when you go to fracture near the wellbore, what you are facing is basically a different set of stresses that do depend on SVSH max SH min, but they also depend on other stuff like Poisson's ratio, like wellbore pressure, etc., etc. So that means that the fracture may not initiate the way that you expected it to initiate. And then it will have to twist to get to the way that is dictated by the far field stresses. In this case, we said it's something very bad because it creates a near wellbore tortuosity. This is like fluid complexity, let's say, or fracture complexity in the near wellbore region. In that case, the how you call it, this near wellbore tortuosity will cause some issues, like when you are doing completions, when you are stimulating, you may end up having what we call screen outs. Now, many stages will end as a screen out. You end up in a situation where the prop pump bridges and you cannot overcome it. So you're applying a lot of pressure on the surface as much as you can pump, but you don't transmit that stress down hole. In that case, if it happens early, it's bad for your frag job. And then the other problem, it would be like the result of that would be you make a frag job, it doesn't produce after the stimulated well, after the frag job doesn't produce what you expect it to produce before you went to fracture. And the reason that is near wellbore fracture tortuosity. Another problem would be fracture fluid communication across stages. And there was a paper in 2015, Barry and Miskimins. Barry is an independent consultant who wrote a software called Gopher, Gohfer. HF stands for hydraulic fracturing something. And he was the software was bought by Halliburton. I don't remember what year now. And Ms. Kimis is the chair of Colorado School of Mines, Petroleum Engineering Department, and also at the same time, the president of the Society of Petroleum Engineers. She's going to be visiting our campus in something like 2 weeks. But anyway, what they did is that they took data from a tracer test run during a frag treatment, and they found fluid that was used to stimulate stage 1 appear in stage 2 and stage 3, and then fluid used to stimulate stage 3 appearing in stage 2 and 1, and then fluid used to stimulate stage 2 appearing in 1 and 3. And I'm going to show a picture of this result at a later stage, in a later module 3 probably. But ultimately, what I'm trying to say is that longitudinal fractures in the near wellbore region and the near wellbore tortuosity that they are triggering, it can cause a lot of problems to your hydraulic fracture treatment. We talk about the stresses in the near wellbore region, a version of those near wellbore stresses that has static pore pressure after Hubbard and Willis. With some of my graduate students, we go one step forward and modify those stresses for elasticity, which is something that you learn in geomechanics. And actually, it's the Heimson and Fairhurst version that we are using. For the class right now, I think Hubbard and Willis makes sense. And we talk about what happens when you initiate a longitudinal fracture versus a transverse fracture, etc., etc. We talk about drilling-induced tensile fractures that are basically the same DNA as hydraulic fractures from stimulation treatments. Those are induced during drilling naturally. Moments where your mud weight is higher than what it needs to be, they are registered on image logs as drilling-induced tensile fractures, DITF. The opposite of that is shear failure, which happens on the other way, on the other angle, orthogonally to DITFs, and we call those wellbore breakout, borehole washout, or wellbore washout. They mean the same thing. And it makes the hole look more oval. So if you see a vertical well that looks like oval shape, the long side is always along SH mean. For a horizontal section, you need to decide if it's gonna be between SV and SH max, depending which one is the smallest, least compressive of the two. Okay, I'm sharing the right screen and I'm recording. What else? Then we took the equation for longitudinal drilling induced tensile fracture, and we saw that we back calculated or back derived an equation that we had already seen before. And I remember I had told you when we first saw it that we were gonna come back to it. And it was now you saw how it was derived. So it's not like I didn't throw it at initially. I threw it at you just as it is, and I told you this is how you use it. But now you know where it came from. Then we saw an example problem that was very useful in a sense that it gave us enough information to apply a constraint on SH max, an upper value and a minimum value, and from that understand what kind of stress regime you have. The answer was normal. And I think more or less this is where we left the class last time. And I told you we're going to see a short video on YouTube today, the next lecture, where it shows how does the fracture orientation varies. And this is really, how do you say, another conceptual experiment. It's like a demonstration experiment that they use even at high school level to show how the fractures open, geophysics people. So, or magmatic intrusions. By the way, magmatic intrusions, what they call dikes, is tensile failures, okay? They are fluid-driven tensile failures. It's no longer fracturing fluid or drilling mud, as in the case of DITF, is magma, okay? Molten rock. So if I tell you dikes, if I tell you hydraulic fractures, if I tell you DITFs, it's the same thing. It's the same sort of idea. You need one of the stresses to become more tensile than the rock's tensile strength, basically. So this here, let me try to open this file if it still works, the link. I think it works. Okay, we don't care about about I don't want to see the skip. Okay, it has music, we don't care about it, but they have a jar of gelatin from its color, and I have experience with gelatin experiments. I know it's a very low concentration one. So it doesn't really resemble rock. If you want to make it accurate, to accurately resemble rock, you expect it to be like yellowish. This is what your TA is doing. Like if you see his sample, they are very yellowish. This is more like greenish, yellowish. It is less. I think it's good enough for this purpose of this experiment, but it's not scientifically valid. But anyway, so this person is gonna come down with a straw, which simulates the wellbore with some color fluid like juice, and he's gonna inject this juice at a shallow depth. Okay, let's see. It goes in, and look, goes only to that depth, and he's gonna inject it from here. If I can write, I will write with the mouse because I don't have a functionality here to write with a pen. So bear with me. So here, at this point here where he's gonna inject, the stresses acting on the injection point is a stress from, I'm gonna make this a dot, as in from outside of the screen inside. We'll call that a confining stress or a horizontal stress. Let's call it sigma H O R don't worry about SH max or SH min. Assume that SH max is equal to SH min. Okay, it's something like this, a certain value. And then the overburden is this much. The weight of this gelatin is basically sigma V. Okay, so now the fracture will initiate a certain way. Look. Okay. And I'm going to ask you now, is it transverse or longitudinal? And the answer for that, the answer for that would be, I would have asked if there was audience, but it's how the how the fracture is aligned with respect, oriented with respect to the wellbore. So now the wellbore is like this. The fracture, let's just say, is like this, idealistically speaking. You see, it's at right angles to the wellbore. So it's transverse. The answer is transverse. And that's what I draw with blue normally. But for this to happen, remember, let me go back to the yellow color. Remember the fracture? Let me just 1 second. We said blue, transverse. This is the fracture. Okay. Now the fracture opens doing work against the least compressive in situ stress. So it works against this stress. So the way the fracture opens tells me that S horizontal, the confining horizontal stress is bigger than sigma V, because sigma V is the least compressive. We are operating against it. You are doing work against the overburden. You are lifting the overburden. So we get the transverse. Okay, now if we go deeper, he's gonna go with the straw again deeper. Okay, he's gonna poke deeper in the sample. And now he's gonna get a fracture that looks a little bit different. Okay, and when he's gonna turn the jar, you're gonna see a certain view that will convince you. This is the view I saw that convinced me that, okay, this is certainly a tensile fracture. Okay, because well, it's a longitudinal tensile fracture. Why is it longitudinal? It opens, let's see, the wellbore is like, oh God. The wellbore is like this. The fracture is like this. Its plane is in the axis, parallel to the axis going through the center of the well. The plane is parallel to that pink axis I drew. Okay, so this is basically a longitudinal fracture. Now, let's see. Now you have, as before, you have horizontal acting like this into the screen. I'm doing a dot, so from outside inside. And then you have the overburden. Basically, it's all this sigma V, the weight of that gelatin above me, okay, which is much bigger than before. Like it's 3-4 times bigger than before. Okay, so by going deeper, I increase the overburden above me. So my SV increased. So now let's go back to the side view that I liked, that makes you understand that this tensile fracture, all of them are tensile fractures. The one we saw earlier, the transverse, was also tensile. So clearly I'm opening in this direction. So now it tells me that H sigma V is bigger than sigma H O R. Okay, now by going deeper, my SV increase overcomes the horizontal stress, and now the fracture opens against horizontal, so basically longitudinal. It becomes a longitudinal fracture or an axial fracture, as some people like to call it. Or in this case, it would be a vertical fracture. The problem they used to call them vertical and horizontal fractures before because all the wells were vertical. So a vertical fracture was longitudinal to the wellbore. But a vertical fracture from a horizontal well is actually transverse. So it can be very confusing. That's why we switch nomenclature we describe the fractures the way they are oriented with respect to the wellbore, not with respect to space per se. So now we are opening against, now S3, sigma 3 is no longer a SV, is sigma hor, the horizontal. So this is a very important video. And it goes on. I think he has some other experiments he's doing, but I don't really care about those that much. And I don't know if he understood it, but I wrote a comment here in the video 5 years ago. And when I think I had graduated and I was waiting for my papers to come over so I can start working. Somebody wrote that is not in any way what hydraulic fracturing is. It's hydraulic jelly donut injecting. Don't think this person is either joking or they don't know. Oh, it sounds like I mentioned. I talked to him. But anyway, I gave an explanation of what I basically explained a few minutes ago here at the comments, but it's not my video. So, and I did not do this experiment myself. I know it's very easy to do in the lab, and I know Kalu has done this work before with outreach activities, etc. Now, you saw transverse and you saw longitudinal. You saw how they look like. Now, how do those look like in an image log? The answer is like this. Initially, it's a little bit hard to understand what which is which, but ultimately, once you train your eyes, there is people who are very used. They work with image logs every day, and they make much more complicated observations than what we are trying to do here. Here, I'm just telling you, wellbore breakouts looks like a black shade, and a solid, dark, distinct black line, narrow line is DITF, as we see here. So powerful diagnostic tool, powerful diagnostic tool. Dark patch is the well-bore breakout, and then dark line, darker, narrower line is the DITF. So it can be everything that we see here. The DITFs that we see here are longitudinal to the well-bore. They can be transverse. They can be transverse. They can be transverse. And as you saw in the homework, you have an example where the fractures are transverse. It's much better looking, much clearer, and it has a much, much more powerful diagnostically speaking. It's going to help you constrain the SH max properly. Okay. Now, of course, everything in between, an oblique fracture, what the geologists call an echelon, an echelon-like fracture, N is oblique to the well-bore is very possible. This is a section from a vertical section. It's from one of my papers, but it's not my picture. They gave me permission to use that picture. Cameron Miller from SLB gave us the permission to use them because this you can see transverse very well and you can see the longitudinal very well. Now, transfers are more rare. That means they are more powerful diagnostically speaking, as I mentioned earlier. And their observation has been used to constrain the magnitude of SH max within certain ranges. And that's what you're going to do in the homework. Now, example problem number 7. Use the stress polygon concept to indicate the range of in situ stress states where transverse DITFs will be initiated from a vertical well under fully balanced hydrostatic conditions, where PW is equal to PP, which is equal to 0.43 SV, and with mu equals to 0.6 and the Poisson's ratio ni 0.3. You can neglect the rock's tensile strength, so assume it's 0, common practice. And okay, so now you need to use the polygons to indicate the range of in situ stress states where transverse drilling induced tensile fractures will be indicated. So draw the stress polygon for PP hydrostatic pore pressure and mu equals 0.6. Then add a red line for sigma zz equal to 0, which is basically sigma zz equals to minus t. Let me want to use yellow. So I use orange. Minus t. And then a blue line for sigma zz equals to sigma theta theta. Now, both of those, I should really do it like this at r equals rw. Okay. Now, I'm not the one who did these plots, so I don't really use my own color scheme on that. But ultimately, they do the same thing, just different colors. So you draw these polygons, and then shade in yellow the region between those two lines that indicate the range of in situ stress states where transverse DITFs are initiated. Let me clean. So we have the red line for sigma ZZ where R equals RW. And then we have the blue line where sigma ZZ equals to sigma theta theta. Okay, the region between those two lines, and you can use trial and error and points to verify that, is the region where the conditions is true. So the yellow region, let me write, I guess, in yellow here, is where sigma, oh, no, bad idea. The yellow region is where sigma theta theta is equal to sigma z z, and sigma z z is equal to 0 or minus t, which is 0 again. So that yellow region, both of those conditions are true. If you understand, in front of the blue line is where this is true. Sorry. I should make, sorry, I shouldn't use equal signs. In front of this line is where, annotate this part in front of the blue line. Is where this is true. Sorry. No, I was right, sorry. This is true. The sigma ZZ is smaller than sigma theta theta. And you don't need to understand it graphically. You can just check it. Use a point here, add it into your equations, and check it. You'll understand what I'm saying. And then this part here, in front of on the left of the red line, is where sigma ZZ is smaller than 0. And we said that 0 is basically minus t. So the region that the overlapping region from both of those lines is that yellow region is where both conditions are true. Okay, when those conditions are true, axial stress more tensile than the tangential strength, and the axial stress more tensile than the tensile strength of the rock, you get transverse fracture initiation to initiate. Transverse DITF to initiate, sorry. Now, imagine if we are more flexible, we say, okay, what if I want to see mu equals 0 0.4, 0.6, 0.8? I don't want to just do 0.8, 0.6. So what is going to happen is at 0.4, polygon becomes smaller, yellow region disappears, okay? Because this is the region for mu equals 0.4. Very small polygon from 0.6 that was before. Now for 0.8, polygon becomes bigger. And it basically, the polygon is bigger, and then you have a bigger range. The range of the stresses, they become much, much more than what you had at 0.6, right? Therefore, if you change the mu, it's going to change the answer to your problem, even if we are talking about a graphical solution, of course. Now, imagine if we put more complexity to it, we change the Poisson's ratio. We don't use 0.3 that I used before. You use 0.26 and 0.34. that will shift the lines. It won't affect the size of the polygon, but it will affect the lines. It's gonna make the lines go, the higher the Poisson's ratio makes the red line move to the right and the blue line to move to the left. So it will inevitably also impact the size and existence even of the yellow region between the overlapping region. Yeah, I guess the best way, it sounds like for a very big region, for a very big yellow region, you want a bigger Poisson ratio and you want a big mu, and also you want a smaller pore pressure. We don't see that, but the pore pressure also affects the size of the polygon. The smaller the pore pressure, the bigger the polygon. Now, yeah. Now, from a diagnostic perspective, I want this yellow line to be, the yellow region to be as small as possible, because that's what I will use to constrain my SH max. I'm gonna read that from the yellow, from the vertical axis on the right, okay? And this is what you are also gonna do in the homework. You are gonna read the range on the vertical axis and see how it ranges. So you want a small yellow in that case if you have observed transverse drilling induced tensile fractures. But you don't control these, you are not gonna be, you may not be lucky, you know? Okay. You know what? I think we can go over the homework today. Since we are we finished the module. So what did we learn in this module? Linear elasticity, moduli, and interrelationship. We learned the in situ stress states and the Andersonian faulting theory. Those should all be reviewed from geomechanics. We learned how to estimate the overburden or SV and SH mean. If SH mean is the smallest of least compressive in situ stress. And we talk about stability to shear slippage along pre-existing faults using the stress polygons, which is, again, not a new concept for you guys. Then we talk about near wellbore stresses and their equations, wellbore stability, borehole breakouts, and DITFs. And we also talk about approximating the SH max magnitude, example problems 0.6, 0.7, and as you will see in homework 1. So since we have some time, let me go over homework 1. So we will start next week, next Thursday, we can start the module 2. By the way, the mix-up, I thought I will need 11 lectures to go over module 1 or be done by lecture 11. But now we are done in lecture 8 because this semester we changed the class to 75 minutes instead of 50-minute lectures. That's why. So our pace is good. It's just when I don't have audience, there is nobody to stop me. I always feel like I'm rushing. And if there are any questions, I don't know them. I need to guess them. So yeah, feel free to use my office hours, email me or the TA, and we'll clear up everything for you. So let's see the homework, which is due homework. Oops. No. Where is it? Blackboard. And then well completions. So I don't see it like you are seeing it. But anyway, let's go student preview since we are here. Start preview. This is what you are seeing, I think. If you come to assignments and you go in, you will see homework 1. Okay, due on the 17th, actually. Oh, 17. What is the 17th? I thought it was the 16th. Oh, 17 is Tuesday. Okay, perfect. So I don't need to delay it. You have another lecture as well. Good. Sorry. When I came back from my trip, I had a lot of stuff to do that Saturday and a very long to-do list, and I don't remember everything on top of my head. But anyway, this is where you're gonna find the homework. You're gonna submit it through that portal, that very same portal. And there is assignment submission guidelines here. But if you have any problem, please let me know. So let's go and see the homework. Oh, what a long homework. Okay, background. Good knowledge of the local in situ stress regime is essential in well completions design, especially reservoir stimulation. Quantifying SH max is a more challenging task compared to quantifying SV or SH mean. Overburden calculations, i.e., total mass of the overlying rock layers, can provide a decent SV estimate, while leak of testing can provide a rough approximation for SH mean from the ISIP, which we mentioned earlier in this class. Nevertheless, the elasticity theory can be combined with the observation of drilling-induced tensile fractures to constrain the local magnitude of SH max within a range. The smaller, the better. Like I said earlier, the smaller the yellow part, the better. This can be achieved graphically. So, problem statement. Transverse drilling-induced tensile fractures were observed from image logs recorded in vertical or from a vertical well A. The Poisson's ratio and friction factor of the local rock formation is 0.28 and 0.65 respectively. Leak of tests from well A indicate SH mean to be 0.91 psi per foot, while overburden calculations suggest SV is 0.93 psi per foot. Okay, notice 0.93, not 1 psi per foot. So very different, quite different. It can lead to different results. Compute graphically a range for the magnitude of SH max, assuming balanced drilling conditions with hydrostatic wellbore and pore pressure gradients, PW equals to PP, which is equal to 0.43 psi per foot. That means giving you information, and I say you need to do it graphically. So you're gonna basically have to build a polygon and add some lines to it. Hint, the criterion for transverse drilling-induced tensile fracture initiation is that the axial stress sigma ZZ at the wellbore radius R equals RW, or on the wellbore radius, is simultaneously more tensile than the tensile strength of the rock, T, and more tensile than the tangential hoop or circumferential stress, sigma theta theta, also on the wellbore radius at the same location. You can assume T equals to 0. It is recommended to start by drawing a stress polygon for the given inputs and then incorporate the conditions for transverse DITF initiation. No additional information needs to be extracted from figure 1 to complete the assignment. I'm saying that because in the past I had people taking this figure, which is basically the image log, and getting their protractor trying to measure the angle of the fractures, their azimuth, etc., etc. No need for that. No need for that. This picture is basically to say, oh, look, here is my proof that I had seen transverse drilling induced tensile fractures. And this is a picture I was telling you earlier that makes the drilling induced tensile fractures, the transverse ones, very, very clear. You see? Oh, I shouldn't use orange. Let's use green. Okay, straight, transverse. Very evident. Transverse drilling induced tensile fractures. Okay, so that's the whole point of the figure. You don't need to use it anymore. If you believe me that there were transverse drilling induced tensile fractures from a vertical section, then we are good to go. So, okay, I want to go up. What I'm telling you about this figure is that basically the conditions for drilling induced tensile fractures to be of transverse orientation. So what I wrote earlier, sigma z needs to be more tensile than 0, which is minus t basically. You don't need that. And then at the same time, sigma z needs to be more tensile than the tangential stress at the same location. All of them are at R equals RW. Okay? So what I'm basically asking here is for you to draw a polygon. First, you're going to draw a polygon for the conditions given, hydrostatic, pore pressure, and wellbore pressure. Mu equals to 0.65. Poisson's ratio 0.28. Sorry, you don't need Poisson's ratio for that, but you need it for other stuff. SH mean is 0.91. You don't need that, but for now, SH mean is gonna be important. But yeah, remember that you are dividing not by 1, but by 0.93 now. Except when you actually plot the polygon. Well, when you plot the polygon, you have to use pore pressure. In the example in class, we used 0.43, but it was 0.433 psi per foot divided by 1. Now it's no longer divided by 1, it's divided by 0.93. So it would be something bigger than 0.43, right? It would be like higher force, like 47 or something. So the idea is that you will build a polygon divided by SV, and then you have now the polygon will have a dotted diagonal, and then it's gonna look like this. This would be 1. This will also be 1. Then you are gonna draw the 2 lines. One line for this and one line for this. So you are gonna have a line like this and a line like this. And then in the middle, you are gonna have the yellow region. Now, I'm asking you to measure SH max. If I have a yellow region going from this value to this value, that's my range. However, now you are giving another information that can help you narrow that yellow triangle even further. And how are you gonna do that? You're also given SH mean. You have SH mean as well as SV. So you can plot another line, an extra line on this plot that can help you make the yellow triangle even smaller. And in that case, if you make the triangle smaller, but you will be able to constrain this range, make the range the yellow. I shouldn't be writing with yellow color, but make this, like add another line, make this region smaller, so this one will also become shorter in height. So in that case, you will, this is what I'm expecting you to do. And if you do it right, you're gonna be able to constrain the SH max within a very short, narrow range. Yeah. This is the homework, and from my understanding, after you leave geomechanics, you are already able to build a polygon. And now you just add 2 lines to it. And in this homework, you have information to add an extra line, a third one. And then based on the way those lines intersect or overlap, you will see the yellow region. It will be a tiny one. So you can basically make the SH max be constrained within a very narrow range. That about homework 1, which is due on Tuesday. Yeah, tomorrow I'm gonna have office hours, so try to go through it, and if you have any questions, come over. Is it? I think we started at 30 and now it's 22. That means 30 minutes and 22 minutes. It's really a 75-minute lecture, but I think I'm gonna cut it short, or shall I talk also about I think I have time to talk about I have time to talk about the term project, but I don't want to. I want to upload some stuff and then I talk about it. So maybe next lecture we do that. It was customary when the class was only 50 minutes. We finish module 1, we do the homework, and then we talk about the project. And then we carry on with module 2. Because then there is the second homework, which is actually easier than homework 1. And after that, we have the exam, the first exam. And then, yeah, but I can have the material for the project ready for Thursday. And then we proceed accordingly. But yeah, start the homework early. It's not a lot of work. It can be confusing having to draw the polygon and everything, and you might need help. That's when you need to reach out to Kalu and me, and then you need to add the lines. Basically, so think about it. The polygon is the diagonal and 3 lines, so 4 lines. And then one line for sigma zz equal to 0, so 5. Another line for sigma zz equal to sigma theta theta. This is line 6. And then line 7 is going to be the new one, which you have to think about it, but it's easier than the other lines because you have the information. SH mean equals to 91, 0.91. And SV is equal to 0.93. So if you combine the two, you can get a value for like X equals something, and it's going to look a certain way on the plot. So you are going to be able to constrain the SH max better. And yeah, you'll be able to read a very narrow range on the y-axis. All right. Okay, so I stop sharing. No, let me share. No. Okay, so I guess I will see you on Tuesday or tomorrow if anybody visits me during office hours. Yeah, start the homework early, please, and you should be okay. Thank you very much. Have a nice rest of your day.